Today's webinar is like all of our previous webinars. It's a request fulfillment from our many attendees over the past several years. And, a pace, by the way, which has been increasing substantially and for which we are extremely proud and appreciative. But anyway, the request from all of you centered on providing much more detail on the engineering behind proper boiler feed water delivery, not only from the feed tank to the boiler itself, but from the system as well. And so when we started thinking about the best way to address the issues, we thought it would be good to involve pump experts to assist us in the development and the delivery of the program. And we chose Grundfos Pump for this task. Grundfos is a company that we have used on our boiler feed equipment systems for many, many years. And we found them to be extremely knowledgeable and most helpful, be it in assisting us with our own technical issues or assisting us with the delivery of this program. So I'm really most pleased to welcome Jim Sweeteye as a co-presenter for today's program, wherein we're going to be covering the following topics. I thought give you a brief review of a typical steam system, just to kind of get us all oriented in terms of what the holistic view is going to be. And then the boiler size range, the pressures and the types that we'll be addressing today. We're going to be focusing in on boilers and pressures that are most commonly used, that we run across most frequently. And then the methods and importance of capturing condensate for boiler feed. We're going to touch on that. Typical pumps used for boiler feed water discharge. And we'll look at typical piping methods that would be used in conjunction with these pumps. And then Jim's going to get into pump sizing criteria. What goes into sizing a pump for a particular application? And then going to be calculating the base flow. That's where we really start. And then we want you to really understand TDH and NPSH, the total dynamic head and net positive suction head. We'll be getting into details about that. And then we're going to size a pump for a specific application to take you through that criteria and the sizing methodology and the logic that we use. And then we're going to take you to reading the pump curve, and that's for the final selection. We've come up with a size, we've come up with the base flow and things like that, but now we want to make sure that we're in the right place on the curve, and Jim will take you through that as well. And then, of course, as we normally do, we're going to give you a summary and then Q&A. Well, as mentioned in the agenda review, I just wanted to quickly go over a typical steam system, wherein steam from the boiler, which is nothing more than water converted to gas, steam is a gas, and it flows through the piping highway, serving various users, as you can see on the screen. And then upon giving up its latent energy to the process, it then condenses to water again, where it can be either wasted or returned to the boiler room to be used as feed water for the boiler. The whole point is, this condensate is really valuable stuff because it contains valuable BTUs, sensible energy, and also chemicals, which if returned can save considerable operating cost if this factor is really thought through wisely. And I've talked about this in previous webinars, so I'm not going to beat it to death now. But that said, what we are going to be focusing in on today are industrial high-pressure steam boilers with a horsepower range from 100 to 1,200 horsepower as packages. Now, we know that they go higher than this in horsepower, but this is a very popular span to zero in on. And then we're going to be looking at design pressures from 150 to 500 psig, 500 pounds. And as far as feeding these boilers, we're going to be focusing in on vertical multi-stage pumps. But knowing full well, regenerative turbine pumps would meet this criteria too, but the vertical multi-stage is the most popular. So with the range of boilers we'll be looking at today, covering 100 to 1,200 boiler horsepower and design pressures to 500 pounds, our boiler selections most likely would be either a fire tube boiler with an integral or a gun-type burner, or an industrial water tube, also known as the IWT, and it's depicted on the screen now to the right. Now, for quick clarification purposes, the fire tube boiler consists of a shell, tubes, and a furnace. The tubes in the furnace, of which they're all submerged in water as the hot gases traverse through them, giving up their heat to the water, and then creating steam upon reaching the saturation temperature of that water at that pressure, at that given pressure, whatever it might be. Now, note the multiple passes and the tube sheet welded to each end of the shell and to which the furnace and the tubes are attached. Now, the industrial water tube boiler, on the other hand, has the water in the tubes, and the hot gases traverse around the tubes, heating the water and then creating the steam that I spoke of. That steam is then released in the upper drum before exiting the steam nozzle at the top of the drum, and then leading to the steam header connected to the steam piping system that I just showed you in the beginning. Now, here's a closer look at the tubes in a typical water tube boiler and how they are joined to each other, forming the gas tight seal so the hot, radiant, and convective gases can come in complete contact with the heat transfer surface without bypassing. So, those are the boilers that we'll be referring to today as we delve into the engineering principles associated with the proper water feeding of these boilers. And as I just mentioned, returning condensate is extremely important for economic reasons, for sure, but for environmental reasons, too, as returning condensate saves precious water. You know, it's a commodity that we always took for granted, but are becoming more and more aware of today as to its finiteness. Which brings me back to my steam system slide and the high-pressure steam which has passed through a pressure-reducing station, a PRV valve, and has also reached the end of the supply header. Now, that's the red line at the extreme right top of your screen. Note the steam trap below that header discharging into a condensate return line, and then following that large blue arrow, dumping this condensate into a receiver with pumps, as you can see, which are used for pumping this valuable effluent back to the feed water tank in the boiler room. Now, these condensate return pumps, they're normally vented to atmosphere and limited to no more than, let's say, 200 to 210 degrees. And the pumps are also low NPSH, net positive suction head, and Jim will discuss this a bit later in much more detail. But the main thing to remember is if the condensate does not have sufficient motive force to propel itself back to the boiler room, a transfer station, such as you see here, has to be employed. Now, the other thing we often run into is when we have high-pressure condensate dumping into a low-pressure return line, it causes all sorts of problems that we really don't have time to get into now, but suffice to say, precaution is necessary. And what we commonly find as a resolution to the problems is the high-pressure condensate first goes into a flash tank, as shown in the lower center of the diagram. Now, in this case, about 20% of the condensate will flash and be vented to atmosphere, thereby allowing the remaining 80% of the low-pressure condensate to enter the condensate line destined for the boiler room. Or, there's another option besides venting the steam from the flash tank. Why not capture the valuable BTUs contained in the flash by piping the resultant steam to a low-pressure use, such as, let's say, it's a unit heater, or maybe heaters, or possibly to the DA in the boiler room, thus providing otherwise wasted steam for the deaeration process. Now, I want to hastily add, though, if one of these is the choice, the steam has to be coming from a non-modulating load in order for that supply to be constant. And then there's another option. Combine the flash tank with an economizer, which is pictured on the right of your screen, and use for preheating cold process or maybe boiler makeup water before the condensate is returned to the boiler room. You know, it makes a lot of economic and, of course, environmental sense. Okay, now we have the condensate back in the boiler room. Where do we put it? Well, it goes into one of two places. Either into a vented receiver, as shown on the left, which, by the way, can only hold water at or below 212 degrees, or, anything hotter than that is going to flash the atmosphere. Or we put the condensate and any makeup boiler water into the deaerator, a type of which is shown on the right. And as you'll note, these are pressure vessels operating above atmospheric pressure, and therefore are capable of removing much more oxygen and carbon dioxide than the vented receiver, even with a steam diffusing tube, because of the elevated temperatures that these deaerators can provide. Now, I might add, too, all these deaerator packages come completely equipped with the tank and the stand, plus everything that you see that's highlighted in red, and including all the control and interconnecting wiring. So, indeed, they are complete packages. You'll note I mentioned when I showed you the deaerator just a couple minutes ago that I said it was one type of deaerator. And that's because one can actually choose from three different types. The first is shown on the screen now, and it's referred to as the spray type for obvious reasons when looking at the cutaway and seeing the spray cone assembly, which is located in the top portion of the holding tank. Then there's the tray type of DA, which is pictured here. Now, it's normally used in larger steam applications and where the boiler room has ample height. The spray type DA that I just showed you is used in those applications where headroom is a problem because it limits the headroom requirement because of its integrated design. And then finally we have the column type deaerator, which is similar to the tray with its separate tank on top for deaerating, but it is the smallest in terms of deaerating capacity. As you can see, needs height in the boiler room to accommodate the column on top of the storage tank, just like the tray. So there you have a very brief overview of the types of feedwater systems used for storing boiler water as required through the evaporation process in the boiler. I might add, you can get much more detail on these systems and on other valuable pieces of information concerning the corrosive gases these systems are intended to eliminate by viewing the recorded presentation posted on our websites entitled Boiler and Boiler Feed System Basics. Now, having said all this, there's one other option I wanted to highlight before turning the program over to my associate, Jim Sweeteye, for the pump discussion, and that is the use of a high-pressure condensate receiver. You'll recall earlier when I said we often find occasions when high-pressure returns are going to a low-pressure return line and need to be flashed off before doing so. There's another option. Take those high-pressure returns right back to the boiler room using its own motive force and dumping them into a high-pressure return tank. As you can see, these returns don't need to be deaerated and are pumped directly into the boiler from this tank. So in this case, the high-pressure condensate return tank becomes the main boiler feed tank, and it's supported by the deaerator for maintaining its level with deaerated boiler water coming from low-pressure returns and or raw makeup water. So it saves a lot of energy and chemicals when we find the suitable application. So it's worth keeping in mind. So there you have it as far as the options for boiler feed water tank systems. The types of boilers that we'll be applying these systems to, and also some ideas on capturing some often lost energy through prudent handling of both high and low pressure condensate return. Now, to tell you a bit more about the actual delivery of this boiler water into the boiler from any one of these boiler feed systems, whether it be vented, whether it be of the three types of deaerators, it's my associate from Grundfos Pumps, Jim Sweeteye. Jim?
To all of the attendees. Thanks, Steve, and thanks to all the attendees today. We'll try to make this nice and informative for you on the boiler feed pump side of the equation. Before we actually go about selecting a boiler feed pump, I want to mention that in larger applications, it's pretty common to install multiple boilers in parallel next to each other, as shown here. There's a couple different common designs for the feed water pumping systems for these multiple boiler applications, and we'll take a brief look at each of them. The first method is known as direct feed for multiple boilers. If you'll notice, there's a common deaerator that supplies these multiple pump sets. Each pump set has its own boiler, and individual pumps are for each boiler. Control of the feed pumps we accomplish in the same way as if we just had one pump feeding one boiler. So a very, very simple control arrangement. Now, I do note that in this arrangement, we could be going to a vented feed water tank instead of a deaerator tank, but the principle would be the same. Essentially, you have one pump per boiler. The system's very common, and the reason is it's very easy to maintain and switch out a complete boiler or feed pump. The second method is a bit more complex. We're using booster sets of pumps for feeding multiple boilers. Notice there's a common deaerator, but it could also be a vented feed water tank instead of a DA, but we'll use the DA tank as our example. Now, instead of having individual feed pumps supplying each boiler, if you'll notice here, there's a 4-pump booster set that's supplying water into a common manifold. It's that dark black pipeline vertical in the middle of the page. From that manifold, the water moves to individual boilers through modulating feed water valves on each boiler. When we arrange things in this way, those pumps are they're controlled so we can have constant pressure. Now, and that's different than the arrangement in which you have individual pump sets for each boiler. In this case, we're using the constant pressure to maintain a specified level in the boiler. Now, there's a few cautions to keep in mind with this design. First and foremost, you would never want to add another boiler or another feed pump without very, very carefully thinking through the complete system, because you can easily cavitate a pump and destroy it, and you can dry run it. So be very, very cautious with those booster sets for controlling multiple boilers. Now, we're going to talk about the overall steam boiler system, in which case there are a lot of different pump applications. We're only going to be looking at one today. We're only going to be looking at the boiler feed pump application. But there's collection tank pumps, there's water treatment, the condensate return that Steve talked about a few minutes ago, and so forth. So there's a lot of different applications. The boiler feed pumps we're going to talk about utilize the silver-looking pump in the upper left corner. It's high stage, high head, multiple stage pump. If you look at the two end suction pumps on the right, those are single stage pumps, which means that they only have one impeller, and when you only have one impeller, you get much, much lower head than you would get with what we need for a boiler feed system. And then, by the way, the green pump in the bottom center is actually a chemical dosing pump for metering chemicals in to treat our water. And we won't be looking at any of these other applications except for the boiler feed itself in this particular webinar. Now, when we talk about sizing a boiler feed pump, there's some complexities that come into the equation. We have to take quite a few different things into consideration, and what this webinar is going to try to do is sort that all out and try to simplify it. So what we want to do is choose the optimally sized boiler feed pump. We don't want it to be oversized, and we certainly don't want it to be undersized. Now, there's a number of concerns. This is where the complexity comes in. A number of concerns that we have to account for to make sure we have safe operation. A steam boiler is a pressurized tank, And we have to assure there's always the correct amount of water in it so there's no boiler meltdown. And because of that, and the way boiler pumps, feed pumps are sized, one consequence is that the feed water pump has to be sized for a flow that's a certain percentage higher than what's actually needed by the boiler during normal operation. Let me say that again because I think it bears pointing out that the pump automatically is sized for a higher flow than is actually needed. Now, that percentage differs by local requirements, local codes. But there's a safety factor, an oversizing safety factor that we'll talk about in a few minutes. Well, because the pumps are oversized due to that safety factor, that can become a problem when certain pumps are running out on the right-hand side of the pump curve, where that net positive suction head required, Steve talked about, it's higher at the right-hand side of the curve. So when we run out, we can have cavitation in the pump and lead to some severe problems. We also have to really be aware of the deaerator water temperature and the presence of treatment chemicals, because both of those things can have an impact on the materials of construction of the pump and the mechanical seal. So there's some of the complexities that we bump into, but we'll deal with them and we'll show you how that's done. We begin by calculating something we're going to call the base flow rate, and then we have to add some other flow factors to that. But the base flow rate is calculated by using this formula. We take the boiler maximum capacity horsepower, and we multiply that times 0.069 times C. C is a constant. We're going to the boiler maximum capacity horsepower comes from the boiler manufacturer's specification, so that's where you pick that up. The 0.069 is a constant. It just is what it is. But this value C can have a couple different values, at least. One, if you've got simple on-off intermittent operation, you have to use a C factor, a safety factor of 1.5, which is quite a lot. If we have continuous feed, we can reduce that down to a 1.15 factor, but we're still oversizing, so be aware of that. But these are required by codes in most cases. Sometimes a larger flow is specified for on-off operation. The factors can vary quite a lot depending on your geographic location. I've seen factors of up to 2.0. So there's our first step. What I'm going to be doing here is walking you and talking you through all of these steps, and then after we do that, we'll actually apply those steps in a selection exercise. So we just identified the base flow on the previous slide. Sometimes we have to add for something called continuous boiler blowdown flow. Now that's an additional pump flow rate that has to be added to account for blowdown that's used to remove total dissolved solids, TDS, from the boiler water. Those accumulate. Now, this is not always required, and it's not always specified. Adding this flow rate is at the discretion of the owner and the engineer. I'm going to I'll describe to you the process of applying it, but keep in mind it's not always required. The way we achieve this continuous boiler blowdown, we place a control valve on the side of the boiler, and that senses conductivity. Conductivity is a measure of the total dissolved solids. So what the control valve does is allow a certain amount of that volume to be removed from the boiler and just sent to a drain. And that volume is replaced with makeup water that has lower levels of total dissolved solids. The feed pump has to be able to supply that continuous boiler blowdown flow even while it's providing the water needed for normal steam production. This is on top of our base flow. And we're going to be discussing bypass flow in just a moment. That's another factor. But bear in mind this continuous boiler blowdown flow may be required by certain specifications. By the way, just a side note, continuous boiler blowdown flow, you should not confuse that with normal blowdown practices. Those are the ones that occur periodically. And those are intended to remove scale and debris that falls to the bottom of the boiler. That periodic bottom blowdown does not require additional flow from the feed pump like this continuous boiler blowdown practice does. So bear in mind this might be specified. Keep your eye open for it. Next, we have bypass recirculation flow. Certain control methods require this, and some don't. And you can see by the last column in this chart which of the ones do, and it varies by control method. What we do is we put a bypass flow recirculation line in, which you can see going back to the deaerator tank, and there's also a feed valve involved in this. And that flow rate through the recirculation line has to be considered when sizing the pump. Additional flow. And I might be using the term recirculation and bypass interchangeably in this webinar. Both are used. The recirculation of flow, what it does, it assures that some minimum amount of flow is passing through that pump to avoid operation at deadhead or shutoff head. In other words, back near zero flow. That happens during periods of reduced flow demand by the boiler when the feed control valve is mostly closed. Because it's closed, it's putting a higher head on the pump, and that moves it to an operating point that's closer to shutoff head, to deadhead. And we cannot, we should not, we must never operate that pump close to shutoff head for any but really short periods of time. Severe damage can occur. Now, notice not all these control modes, not all four of them, require the use of feed valves and bypass lines. The variable speed pump controls can eliminate those. And that reduces, if we can eliminate this bypass line, it reduces flow, and that's going to help drive down total power consumption costs. Well, how do we determine how much flow is needed? Well, we use this curve. The flow that's going to be sent back to the vented receiver or to the deaerator tank is shown here. It has to be sized based on the pump manufacturer's stated minimum flow requirements for each pump. The amount varies, but it's often based on somewhere around 10 to 20% of the pump's nominal flow rate at its best efficiency point. So, here's a chart. This is one method that's used by one manufacturer to determine what that required recirculation flow is. There's some temperatures at the bottom, and you can see percentages off in the y-axis on the left. We'll actually use this chart in our exercise. So how do we determine the total flow rate needed from that pump? Well, we add up the base flow rate. We add the continuous boiler blowdown flow if it's required, and we add this bypass recirculation flow if it's required. And that gets us at the total flow rate we have to use for selecting the pump. Okay, now, when we're calculating total dynamic head for centrifugal pumps, we have to consider a whole bunch of influencing factors on both the suction and the discharge sides of the pump. And typically for the boiler feed systems, these include the pressure in the deaerator tank, the elevation of the deaerator tank above the pump, friction loss through all the suction piping system, and including a strainer if one's used. On the discharge side of the pump, we have to look at the friction loss through the pipes, valves, and fittings, and we have to look at that elevation difference between the boiler and the feed pump. And finally, there's some safety factor required by the ASME boiler code, and we'll be looking at each of these in some detail in our exercise. That's what's involved in the process. So, how do we go about calculating this? Well, in some of the control methods, like we discussed earlier, there's feed valves that are used in the discharge piping between the feed pump and the boiler to control level in the boiler. And the head loss across that valve has to be taken into consideration, and it can be considerable. So that's a very important factor. Okay, now, total head across for the feed pump. Where do we begin? Well, one method is to use a formula that's based on the highest flow rate for the specific application, and that's determined in collaboration between the consulting engineer and the system owner. The pump has to be capable of reaching 2 points of head. Now, first, it has to meet the required flow rate at the boiler operating pressure plus 3%. So in our example, you'll see a 1.03 factor in that formula. There's our 3%. We have a boiler operating pressure of 130 psi. We multiply that times 2.31 to convert it to feet of head, because pump curves are in feet of head, obviously. We multiply times the 1.03, and then we divide by some specific gravity based on the temperature of the water. Our example works out to 324 feet. So the pump, at the design flow rate, the red arrow in the middle of this curve, we have to be capable of meeting at 324 feet, as shown in this example. But there's a second point it has to achieve, and that's the dead head, or shut-off head. And that's a point that's at least 3% above the safety valve setting of the boiler. Shut-off head, or dead head, is the head the pump is capable of achieving at 0 gallons per minute, back there at the left-hand side of the curve. So, we're going to use this formula, and it looks very much the same, except instead of using the boiler operating pressure, we use the pressure relief valve setting of 160 psi in this example. And if you do the math, it all works out to 400 feet minimum to meet the pressure safety valve setting plus 3%. This pump, a little hard to see, the scale is a little small, but the pump achieves about 425 feet. That's more than the 400 feet required by the specification, so this pump would meet that. So, as a result of this example, you have to size the pump for a head of 324 feet. Some other components we'll talk about. When we get into our actual exercise, there will be a complete discussion of all this stuff in detail. Steve mentioned earlier the net positive suction head. That's a force that's pushing water into the eye of the impeller as it spins. It's Mother Nature's atmospheric pressure and some other things that we have to take consideration. We read the net positive suction head required, it's called NPSHR, off the pump curve, and it looks something like this. In our exercise, we'll go into it a little bit more deeply. Whatever is stated on that curve, generally you need to add 2 to 4 feet of safety factor. And that's an important thing I'll talk about in some detail. Now, there's a formula that we use to calculate the net positive suction head available. So we pick up the required off the curve, but we have to calculate the available, and we have to do this on each and every application because they're all different. And you can see what the 4 component parts are there. When we do our exercise, we'll look at each one in detail. That's how we arrive at net positive suction head available. One of those factors that we need to look at, incidentally, is elevation. And that's the elevation of the lowest water level in the DA tank and the lowest impeller in the feed pump. And that's why the DA tank should be elevated as high as possible above the pump because of that NPSH calculation. By the way, not only is there a potential for a cavitation problem, but if the water level in the DA tank is not monitored properly, we could dry run the pump, and that will cause rapid, almost immediate failure. Failures of that type often happen because of insufficient makeup water refill. So you want to make sure you always add for dry run protection for boiler feed pumps. All right. On the suction line, we have to do some calculations related to net positive suction hit. We have to calculate all the friction losses through that suction piping system, including the strainer. You just, as a rule of thumb, you want to try to keep that friction loss through the suction line piping to just a foot or two in order to reduce that danger of cavitation. You don't want complex piping with lots of bends and elbows in it, and you don't want to undersize suction piping. If anything, you want to oversize it to minimize friction loss. All right, so now we've looked at all the different factors that are involved. Let's actually go through a practice exercise. This is a checklist that we've created for you just as a reminder. You can check off each box as you complete each one of these steps. This is available as a download following the webinar. Next, we have some useful formulas so you don't have to remember these or go looking them up. These are the basic formulas that you'll use throughout the exercise. So keep those things in mind. That's also available as a download later. And finally, for this particular exercise, we want to use this specification. Now, I'm not going to read down through each and every one of these, but I will be referring back to it as we go through the exercise. And also, you can download and print out this specification, so if you want to practice this exercise again on your own, you'll have the specification to be able to do that. All available in downloads later. So, in our selection example, we're going to use this system. In this control mode, notice there's a feed valve in the lower left. Controls water intake to the boiler, and that adjusts itself according to steam consumption. So the fixed-speed pump is set to continuous operation. That means that we need a recirculation line from the pump back to, in this case, a deaerator tank. And when that's used, when that boiler is calling for a reduced volume of water, or maybe not calling for water at all, we need to recirculate that back to make sure the pump does not operate too close to deadhead. So, we'll begin going through the steps. The first step we have to do, look at the spec. It's a continuous duty fixed speed pump with a modulating feed valve and a recirculation line. So we can tick that first item off the list with a red X. And as you go down through these 17 steps, you'll check them off. I'm only going to show this about every fifth or sixth slide in the interest of time, but you'll want to tick these off as you go. Next, we need to calculate the base flow rate. Remember, it's boiler max capacity times 0.069 times C factor. On the spec, the maximum capacity is 250 horsepower. We've got continuous duty. We're going to use a C factor of 1.15. So the base flow rate needs to be 20 gallons a minute. There's your formula. There's the specification points, and there is our base flow rate of 20 gallons per minute. Then we look and we see that sure enough, continuous boiler blowdown flow is required. Not always the case, but it's specified here. So we have to add for that continuous boiler blowdown flow. It's often about 10% of the pump's best efficiency flow rate, but it can vary. And it's set by the water treatment company. Got that? It's by the water treatment company. The continuous blowdown flow, like we said, is designed to remove those total dissolved solids. So it's specified here, so we're going to have to add for that. So the base flow rate's around 20. We're also going to have to be adding for bypass recirculation flow in a moment. That's going to add a little flow. So boiler blowdown flow, again, is approximately 10% of the pump's flow at best efficiency point. So we're going to add 3 gallons per minute for that. Again, the water treatment people will guide you in making that calculation. but in our exercise it'll be 3. Next, we do have to add for bypass flow. Take a look at the chart on the right. Ignore the dashed curve. That's used only for some real high temperature applications that are beyond our scope today. If you find 227 degrees Fahrenheit on the bottom, on the x-axis, read up to the intersection with that solid line and read to the left, you'll see that we need about 20%. Okay, so again, at 227, we read up to the intersection with the line, read to the left, 20% DEP flow, and presuming we can find a pump with a best efficiency point of about 25 gallons per minute or so, then our bypass recirculation flow has to be about 5 gallons per minute. So now, finally, we're in position to take a look at all of the factors that go into the flow rate. We add up the base flow of 20, the continuous blowdown flow of 3, and the recirculation flow of 5 gallons a minute. We need a pump for 28 gallons a minute. So, we've ticked off some of the previous items. Now we tick off item number 5 here on our step. That's the flow rate. Now let's take a look at calculating the head. Here's the formula once again. Boiler operating pressure plus 3%. So we take the boiler operating pressure, specified as 100 psi, times 2.31 to convert it to head, times this 1.03 factor, divided by specific gravity at our temperature of 0.953, and we get a total head of base head of 250 feet. So you can tick that item off your list. Next, we have the suction piping system, and we have to consider friction loss through that. We calculate and determine the gauge pressure in the DA tank, the elevation head, and the suction on the suction side, and all the suction line friction. You can see we've got 12 feet of head gauge pressure. We've got 10 feet of elevation differential, and there's a couple of feet of friction losses. Now notice that the top 2 factors are negative numbers. They're actually working in our favor. That pressure in the tank above atmospheric is helping to push water into the eye of the impeller. That's a good thing. Also, the elevation in this case is working in our favor. So this factor, the suction head piping, actually is a negative 20 feet value. So tick that item off your list. On the discharge side, we have to look at the piping friction as well. And given in the specification was the friction loss through the discharge piping and fittings of just a foot or so each, and that 5-foot elevation. Notice the feed valve. It's set to 15 psi according to specification. We multiply that times 2.31. We get 35 feet. The total head on this discharge side, therefore, is 42 feet. And that's head that we have to overcome. So that puts us in position then to calculate the total dynamic head that the pump has to operate against. So we take the 250 feet total. We subtract the 20 feet from the suction side. We add the 42 feet on the discharge side, and we get a total of 272 feet of head. Now, recall here in step 10 that not only do we have to meet the 272 feet ahead at our design flow of 28 gallons per minute, we also have to think about this pressure safety valve. We have to be 3% above that safety valve setting at zero flow. We know that the pressure relief valve setting is 125 psi from the specification. We multiply that times 2.31, add in the 103 safety factor and the specific gravity. So now we have to be able to achieve 312 feet of head at the deadhead flow rate of 0. So we need to make sure when we pick our curve we can do that. Step number 11 is to take a look at the deaerator tank temperature, which is 227 degrees F according to the specification. Take that item off the list and go on to number 12. We can perform our NPSH calculation. All right, we have 10 feet of elevation of the DA tank minimum water level above the pump's bottom impeller. To that, we have to add the absolute pressure, which is 46 feet. There's a calculation you'll see here. We subtract vapor pressure, which is the tendency of water to flash into steam. Both of those values have been specified. And you can also find charts on those two topics. We won't have time today to go into great detail on that. We subtract suction line friction, which was 2 feet, and that gives us a total net positive suction head available of about 8 feet. Okay, so now we make our preliminary selection. Okay, we know that we need 28 gallons per minute at 272 feet, and we've looked at some of the available curves, and we find this one that falls very nicely right in the middle of the curve. If you look at that red arrow, it occurs at 28 gallons at 272 feet. And then if you follow it up and to the left, you'll see that it's an 11-stage pump. And that would be indicated right here. Color's a little hard to see, but we'll just have to live with it for now. Okay, so yes, this 11-stage pump does meet the specification. I'm going to change that to a different color so it's a little more visible when I use it again. All right, so this 11-stage pump does meet the design duty point, but does it meet the deadhead requirement? Again, if we follow that up, the 11-stage pump, where this top arrow is located here, you'll see that the pump reaches about 350, 355 feet, and that is in excess of the safety valve setting of 312 feet. So yes, this pump does meet that requirement. Next, we need to look at the net positive suction head available. Now remember that design flow and head is 28 gallons per minute at 272 feet, which is here at this upper arrow. The net positive suction head available is 8 feet. So we've got a couple choices down here at the bottom of the screen. There's a solid curve down here at the bottom, and there's a dashed curve. Let's look at the dashed curve first. That's conventional construction. I'll explain the other in a moment. With conventional construction, indicated by this arrow, we have about 7 feet of NPSHR. But remember, to that, we have to add 2 to 4 feet of safety factor. So that means we're at 9 to 11 feet of that net positive suction head required. We've only got 8 available. That will not work. So instead, we're going to go what's known as the low NPSH design. We changed the bottom impeller to improve its characteristics. You find that on the same curve page. It requires a net positive suction head indicated by this arrow, which is at only about 4 feet, somewhere off in that region. Okay, so if we take that 4 feet required and we add in the safety factor of 2 to 4 feet, and by the way, I'm going to use the conservative value of 4 feet. Highly recommended because vagaries of actual boiler installations. So in that case, our targeted NPSHR is 8 feet, 4 plus 4, and that the NPSH available equals or exceeds the required. So therefore, this pump would be acceptable with its low NPSHR stage. Next, we have, there's our requirements, and yes, it does meet it. Then, on step 15, we can indicate by checking off on our checklist that sure enough, we took into consideration net positive suction head and we're in good shape. Step number 16 is to check material compatibility, and we look at the materials of construction, we look at the temperatures, we look at the mechanical seal, especially on the elastomers. We confirm that what's specified will meet the requirement, and we've confirmed with the pump manufacturer that he or she does indeed offer a pump with these materials of construction. And by the way, that EPDM material is good up to around 248 degrees Fahrenheit, so it's pretty useful for boiler feed applications. We make the final specification or selection. We've checked off all the boxes on the list, and we have ourselves a good pump selection that meets all requirements. So we've reviewed all those steps. We've done a selection exercise. Going into greater detail on many of those points was not possible. There are many resources for getting training out there. One of the resources is the Grundfos Technical Institute, and there are many other training resources as well. This particular one, there's about 40 e-learning virtual self-paced courses. There's webinars, live and recorded. There's some face-to-face training. All of them come with certificates of completion, with professional development hours, and many of them also have CEUs associated with them, continuing education units, if you need that. So that concludes my portion of this, and with that, I'm going to turn it back over to Steve. Thank you very much for your time and attention.
Well, thank you, Jim, very much. It was very informative, and here I thought I knew a lot about pumps, and I've been learning a lot from you with our discussions before this, and of course during this webinar, and thank you so much for that. Jim and I got together before this webinar was, as we were putting it together, and we came up with a number of items that we thought would be good takeaways for you to take back with you as a result of this webinar. And the first thing is that, steam condensate is a very valuable commodity which needs to be saved and used as much as possible. Using that, it's like I like to refer to as liquid gold that condensate is. Because remember, a lot of sensible BTUs go into making a pound of steam. As a matter of fact, as the pressure increases, your operating pressure, the amount of sensible energy going in to that pound of water increases, and the latent energy goes down. So that's all condensate that's got not just valuable BTUs that you're saving, that the burner does not have to put back into that water, but also the chemicals and the sewer charges and all these things that are associated with returning this water and using it again. Then, of course, we have most commonly used boilers for process are the industrial fire tubes and the water tubes, which are also referred to as IWTs. High-pressure condensate flash steam can be used for various purposes, such as unit heaters or the aerator. Also, remember, though, when I say that point, that it has to be a continuous supply, not a modulating load. So if you're going to capture that flash steam, make sure it's a constant load. Condensate can be returned to vented receivers or pressurized deaerators, like the spray, the tray, or the column that I mentioned. Sometimes high-pressure condensate receivers are employed. They can save considerable losses. And that would be the high-pressure condensate receiver. As long as it's got that condensate can of its own motive force, its own propellant, and get its way back into that boiler room, put it into a high-pressure condensate receiver. That now becomes the primary receiver for your boiler, and then the deaerator supports it. Boiler feed pump selection involves 17 decision points which need to be carefully considered, and Jim, I thought, went through that very, very accurately, very precisely. Calculating the pump's base flow rate differs from the pump that operates continuously. So it's 15% is the safety factor, and whereas the on-off is a 50% safety factor. Sometimes the base flow rate needs to include for continuous pump recirculation, or as Jim referred to it sometimes as bypass, and maybe for continuous blowdown. The total dynamic head, TDH, is that pressure the pump must overcome to get water into the boiler, and includes the positive pressure at the pump's inlet after suction pipe losses, and the piping losses through the discharge piping before overcoming the boiler's operating pressure. So you need that amount of pressure to get the water in the boiler. You have to take into consideration those criteria, those factors. That positive suction head, NPSH, is the pressure required at the pump's suction to mitigate cavitation. NPSH-A is the NPSH available after all the friction losses on the suction side, but they've been determined in light of the pump's minimum and maximum flow rates. The seal selection for the pump is very important and can vary based on the boiler's operating pressure, its temperature, chemicals, and the feed water. So that pretty much wraps up what we were going to be talking about today for you. Now we will open up not open up the line, but we will receive texted questions from you at this particular point. But I might mention that before we get into the questions that you've texted in, all of these questions that you text in that we can either get to today or not will be posted on our website, which is the same place that you would go to replay this recorded webinar. So there, all the questions and answers will also be posted. And we thank you again very much for attending this webinar today.